Hello, my name's Rick Aldred, and I would like to let you know about my second short course presentation, which will be available soon through Oges, entitled Integrated Petrophysical Modelling of Complex Formations. So what's that all about? In petrophysics, we have many different methods to compute the properties that are needed for reservoir modelling. We also have a lot of uncertainties in our measurements, our methods and our results. So we try to verify each computation with a similar one from a completely different source. For example, we don't rely on a single calculation of porosity from one log if we can use another log or core data to verify our results. For fluid saturations, we usually start with resistivity equations and then use a saturation height function for verification. It's the saturation height function which is then used in the reservoir model. In most homogeneous formations, this is a fairly straightforward task, but in heterogeneous formations, it becomes much more complex. The main problem lies in the fact that most petrophysical interpretations ignore heterogeneities. They use directionless log measurements to determine the volumes of each of the minerals and fluids, as though the formation was homogeneous. They also tend to use directional measurements, like resistivity, as though they were directionless. To get around this problem, we can model the components of the formation, such as the different layers in a thin bed sequence, and account for the effects of formation geometry and heterogeneity. For example, we can model multi-pore systems to see how they affect capillary pressure data, and then build more reliable and accurate saturation height functions. We can also see how the geometry of different layers affects resistivity measurements, often leading to low resistivity pay zones. Now, there are some high-resolution modelling techniques available, where each layer is assessed separately. But when the beds are very thin, or when other types of heterogeneity are present, high-resolution modelling usually generates very high uncertainties. In these cases, it is better to use low-resolution modelling, where components are assessed separately, but rather than define each layer, we determine the relative proportion of each component which is present in the formation. The saturations are calculated from a combination of saturation height functions for each component present. In the final piece of the puzzle, we calculate synthetic resistivity logs from our model and compare them to the recorded resistivity logs. By using different geometries for the resistivity calculations, we can get an idea of the geometry of the components of the formation, even when we don't have core or good image logs. So I hope you can join us for this short course, because you might learn some useful new techniques for interpreting complex formations, get a better idea of formation characteristics, and learn how to predict which low resistivity formations are likely to produce hydrocarbons. Thank you.